So today we're going to look at eye movements. And the reason we're going to look at eye movements is because their purpose is to allow you to see better. So the reason they're there is to improve your vision. And I mentioned last week that the iPhone has this cinematic video stabilization, and one of the eye movements that we talked about, the VOR, does the same thing. So it makes it. The iPhone has this gyroscope in it, and as it moves the lens in the opposite direction, and that stabilizes the image. You have an internal gyroscope, and that's your vestibular ocular semicircular canals and otoliths. And that's your gyroscope, and they in turn move your lens and stabilize your image. So, just to try things out, again, you remember that your fovea is the part of the retina with the greatest acuity. So I want you to look at here. And where's the little clicker? Okay. Tell me whether there's an O or C. I think we'll have to try this again. But keep looking there. Okay, we'll try it again. Hit the table when you see. That's what should we do? Pick it at random. Let's say when you see a C. Okay. Every time you see a C, rather than an O, hit the table. Keep looking at the X though. So you notice that at the beginning there were very few people hitting the table. That's because it was way out in your periphery. Then as it moved closer and closer to where you were looking, and that's where your fovea is, it became easier and easier to make out what you're seeing. Now, the other thing is, the image sometimes moves, okay? So we'll try another test, okay? You have to read this. Now you can read it, right? Now try to read it. You can't, okay? So while it's moving on your retina, you're blind to it. It's only when it's stabilized on your retina can you make out what the words are. So those are some of the things that these eye movements are trying to compensate for. Now, we've developed 5 types of movements to do the job. And each of them serve a unique function. They have a special purpose that and they have the assets or properties. That eye movement has a property that suits that function. So the first one, if we've seen saccades before. So they're the movements that you use to read, for example. As you move from word to word in a sentence, you use a saccade to move to the next word. So if you can, move to someone that's near you, okay? Because I want you to do a sort of a pair up with someone, because you'll have to look at each other's movements, eye movements. Okay, so the first one is saccades, and if the image is off to the side, well, you want to look at it. So you move both eyes, and that points both foveas at whatever image you want to look at, like the words in this sentence. Now, while the eye is making a saccade, it's difficult to see because the image of the whole world is slipping by on your retina at an incredible speed. And it's doing so because this is the fastest of all the eye movements the body can make. You move something like 1,000 degrees per second. So that's your head would move, something like almost 3 times around in a period of 1 second to be that fast. Okay, so gives you an idea. So what I want you to do is to slow it down. Okay, so pair up with somebody and try to make, first of all, have the person look between 2 fingers like this. Okay, and then do it as slowly as possible between the same 2 fingers. Okay, try to slow it down and look at the other person's eyes while they're doing it, while they're trying to make the slow ones. So tell me what you saw during the attempt to make a slow eye movement. Yes. A number of well, they weren't slow saccades. They were fast. That's right. Yeah, you broke the task up at the. It's impossible to make a slow saccade. So what some people do though, they make little steps across, but they're equally fast. Those small saccades, or almost equally fast. So I can make an arm movement from one point to another point, quickly or slowly. So I have a speed control of each other movement that you would do with your body, to move your heads from side to side at any speed you want. But the eye you can't. And we'll look at some of the reasons. We looked at some of the reasons why in the previous lecture, but we'll look at some more of them today. Okay, so no, you can't, and it's a series of small saccades. Now the other one that I want you to do is look from one finger. It's really up close to the nose, and the other, but look at the eyes of the person doing it. Okay, while the person's looking from something really up close to farther away, like these people, critters in the display. You have to put something close and something far. Look from near to far. No. So instantaneously, those jump from one to one. Because if you move your finger back and forth, then the movement will follow your finger. So it's not jumping as fast as it can. Okay, so could you tell me something that you noticed about these movements that were different about the previous movements? One thing that was different. Speed. So how was it different?
Slower.
Yes, they're much slower. Anything else different? What's that? Yeah, yes. In a sense, they look continual, in part because they're much slower. But there's another big difference. Yes. Yes. Yeah. So here they're moving in opposite directions. They're moving in or out. So they're much slower, as you can see here, and they're also moving in towards the nose or away from the nose. Now, the other one is a pursuit eye movement, okay? So that's when you have to pursue a finger or pursue a ball being thrown or bird flying. And again, that stabilizes the image of whatever it is you want to look at on your retina, so you can make out what it is, what type of bird it's flying, what direction the ball is going in, maybe. So now I want you to try the same thing with a friend, okay? First, have him follow your finger as it goes slowly. Don't make it go like this, because he won't be able to follow it, but slowly, back and forth. And then try it without a, so you could see it, you can follow the finger quite, he or she will be able to follow the finger quite well. The eyes will be moving smoothly. Now ask the person to make the same movement, but without the moving finger. It's almost impossible. Okay, you need that stimulus, that movement to engage that MSTL and engage the pursuit system. So you need a moving stimulus to engage it. So instead of a smooth movement, you'll see a series of small saccades. Again, you can't will a smooth pursuit movement. The next one is the VOR. And here we can see the VOR being elicited by the translation of these two critters. And again, that looks similar to the pursuit movement we just saw, but we know it's very different, because here, at least some of the signal is coming from the vestibular system, which is a very short reflex. And the other thing is that it's trying to stabilize the image on the entire retina, whereas before we were just trying to stabilize the image on the foveal part of the retina. Okay, so now I wanted you to compare the pursuit system on your own, if you have a piece of paper to read, something to read. A laptop will do. Laptop screen will be fine. Okay? Well, no, it won't be fine. Backtrack completely. Okay, you need a piece of paper. Okay, so first of all, try to read the text as you turn your head. First, very slowly, and then faster and faster and faster. You'll see that even when you're shaking your head pretty fast, you can still make out what the words are. Right? You get a little dizzy. I said, maybe you get a headache. So don't do it so fast you shake your brain and go get a concussion. Okay, now try the same thing by shaking the paper first slowly and then gradually faster and faster and faster. You'll notice you can't keep up very quickly. Okay, that's because, the VOR has got this very short reflex, just from the ear to the eye. That's a very short distance. Whereas the pursuit system has to go into the eye, to the back of the brain, then to MST, then to MSTL, then down to the cerebellum and out to it. It's got a long way to go. So it's very sluggish. And finally, we have the optokinetic system. And we see that it assists the VOR and it activates the image of the whole world on a large portion of the retina. And it's because of this that it sometimes induces a sense of self-motion when you're sitting in that subway car. Okay, so we've got these four movements, and then we got the eye. So how does the eye work? Well, it's got attached to it 6 eye muscles. And most of the time, they're 60% active, so they're pulling in all directions. But they pull equally in all directions, and so your eye remains stable. Now, if you want to look anywhere but the center, what you have to do is contract one muscle and relax its counterpart. So they act in pairs. So we've got one pair, you notice, is sort of horizontal on each side. Here this way, and here this way. Okay, and then you've got a vertical pair, and then you've got one that turns the eye. You can see it turning. Okay, so that's a third pair. So the obliques are the ones that do the turning. The horizontal rectus and the medial rectus do the horizontal turning, and the superior and inferior rectus do the up and down turning. Now you'll notice for the vertical ones that if you look at this line is vertical in this direction. I've just drawn it on the eye for reference. But as it goes up, it goes a little bit towards the nose. Okay? And that's called intoric. And as it goes down, it moves a little bit away from the nose. The nose is, you can see from down here, is down this part here. That's the nose, and that's the side of your head. So you can see that this one goes towards the nose, this one goes away from the nose, as well as moving it up and down. These ones here do a lot of turning. This one here, again, towards the nose, and it noticed that the eye went down a bit. Okay, so instead of it's not just turning the eye towards the nose, but actually pointing it down a bit. This one turns it away from the nose, but also up a bit. Okay. So now, why do you have the one that turns it? Why do you have these guys? Okay. Well, it's because sometimes you tip your head from side to side. It's for the same reason that you have those canals that sense tipping of your head from side to side. You've got to be able to move the eye in all 3 dimensions, because the head can move in all 3 dimensions. Okay, so we saw the VOR. It has this direct pathway from the vestibular nucleus to the motor neurons to the muscles. And this one here goes to the motor neurons of this muscle. This is the medial rectus on this side, and this is the medial rectus on that side. So it activates both of them at the same time. And so you can see here during the turn that the head turns towards the right, and that activates this canal, and that activates this vestibular nucleus. That activates these neurons here. This is the motor neuron to this muscle, and this activates the motor neuron to this muscle. And both muscles then contract, and the eye turns towards the left. So head towards the right, activates those, opens up those little flaps in your hair, the hairs on your on the hair cells in your horizontal canal here. Now notice what happens though after the movement. The eye swings back to its middle position. Okay? That's not good. Well, that's not what happens in your own movement. Try to move your head, like look over at a friend and then turn your head. Your eye remains deviated in its lateral position. What keeps it there? Well, it's something called the indirect pathway. And this is the pathway, the indirect pathway of the VOR. And the indirect pathway of the VOR goes through this horribly named prepositus hypoglosside. Okay? PPH for short. And what it does is it produces a tonic signal that keeps the eye in its contracted position. Okay? Keeps that muscle contracted and the eye deviated. And it does so through this reverberating circuit. You can see this when the one exponential goes in here, it comes out, but then goes round and round producing more. Okay? So it's something that sort of remembers that your head moved. We'll come back to that guy a few times today. So in summary, there's the signal to these motor neurons goes along two pathways. A large command coming from your vestibular nucleus that moves, rotates the eye during the rotation of the head. And then that's followed by a tonic command that keeps the eye rotated in its new position. Okay, let's look at, that's a VOR. Let's look at saccades. You can see here a simulation. This is where you're looking as you read. And you notice two things, that this word, the word that we're reading, is clear. The words around it are blurred because they're in your peripheral retina. Also, every time the eye moves, everything becomes blurred. So to minimize the time everything's blurred, you make these movements really, really fast. That has, survival value. Nothing can sneak up to you while you're making an eye movement. And you do this by this phasic burst of action potential. By phasic, I mean something that happens only for a brief time. And you're producing, again, something like 1,000 action potentials per second to do that. Now, yes? No, because you wouldn't know, you wouldn't be able to see. But you still have the superior telectricity. Possibly. But you wouldn't sort of have a reason to look at that peripheral retina. You wouldn't sort of notice that something is there, at least not consciously. Mm-hmm. Yes. Well, I have problems reading because I can't make out the word that I'm about to make a saccade to. So I can't decide whether I should move it. You have to be pretty accurate when you're moving from word to word in a sentence. You generally skip the small words and move to the big words because you can figure out but the small words are the as, the from the context. So guess how many saccades we make per day? 1,000, 10,000, or 100,000? Okay. A lot of people are guessing 100,000. Yeah, we make more than 100,000, 170,000 roughly per day. That's an awful lot of saccades. So what produces this phasic response? The phasic response comes from another horribly named structure called the paramedial pontine reticular formation. So basically, it's a structure that's near this sixth nerve nucleus, and it's in the brainstem. And this is the one on the left side, and so this is the middle of the brain coming down between the two eyes, and there's a mirror image of all these neurons on the right side. So activating this moves the eye, makes the saccade to the left side. Activating this mirror image makes the saccade to the right side. Now again, it has two pathways, okay? So from this PPRF, you make a phasic command to rotate the eye, but then you want to keep it there. Try making a saccade to something around you, Well, you make the saccade and you hold it there. You don't want it to slip back to the middle again. You want to keep it there. So to keep it there, the same structure, the PPH, produces a tonic command, and that tonic command holds your new position. Okay, some quizzes. Okay, so again, there's your lesion. Okay, the lesion. So this burst thing is still active. It sends a signal here to the motor neurons. It also sends a signal to the PPH, but that signal from the PPH can't get to the motor neurons. Now this is a normal eye rotation, so this is saccade. And this is the trace one of the traces that this lesion could be producing. So this is normal. These are the possible abnormal ones. All in favor of number 1. All in favor of number 2. All in favor of number 3. Hey, you got it. Good, because without it, you'd drift back to where you started from. Okay, your saccade is normal because this thing goes to this thing and rotates the eye. But when it gets there, there's no tonic activity, and you slowly come back to where you started from. Okay, let's get another lesion here. Now you've got, you notice the X is smaller, so it means it's a partial lesion. This burst comes here, goes to here, but not as much of it can come out. The same thing goes to here, but not as much of it can come out. Again, which of these might it be? This one? This one? This one? Okay, no one wanted to commit themselves. We'll try again. This one. Yeah. Good choice. Yeah. These are small versions of that, okay? So you make a small saccade, you make a saccade, and you don't get there. So what do? You make another one. You don't get there. So what do? You make another one, and you finally get there. Okay? So instead of making it a nice single movement, it takes a number of saccades to get there. And that number will depend on how severe this lesion is. But each of these will be a normal, fast movement. Okay, let's see the next one. You might get, now we have a lesion from the burst neurons to the motor neurons. This signal is fine. It can get into the motor neurons. Okay, so which of these is it? Is it this one? Is it this one? Or is it this one? I think you're right. We all pick this one. Okay, again, this one pathway is fast, but it's missing this one. So what happened? It can't move quickly. You're missing this part, but it'll still get there. It'll slowly creep into its new position. So, we know this much about saccades. Now, the other thing we know about is that we have when we're doing fixation, we're not making an eye movement, okay? And the reason we're not making an eye movement is because these neurons called omnipotent neurons are inhibiting the PPRF, inhibiting the PPRF from producing this burst. So before we can make a saccade, we've got to get rid of this hill. So here we can see this happening. You get an event, something interesting happening in your peripheral superior colliculus. That creates a hill of activity building up. And as this builds up, this hill is removed. When this hill is removed, then this signal to the PPRF is allowed to pass, and it produces that burst in the saccade. Yes? Yeah. When you fixate an object, yes, that produces this hill of activity. That's right. As the hill, some activity appears in the peripheral PPRF, it suppresses this hill. That explain your question? Okay. But if you were thinking ahead, if you might have thinking ahead, you've still got a problem. You've got this burst happening. What stops the burst? Okay. Your PPRF is being activated. What stops it? Now, when you think about it, a saccade of about 20 degrees, so that's a little bit off from your periphery, will take something like 50 milliseconds. A bigger saccade will take maybe twice as much, but not much longer. Okay? So these are very fast things. So what terminates it? Well, one possibility is visual feedback. So it could be something coming from the eye. And that's one possibility. The other possibility is something coming from the muscles. Okay. And for a long time, many people thought this was true, but then they removed all the afferents coming from the muscles, those muscle spindles, and the saccades were still accurate. They stopped where they should be. So vision, I forgot to say this because vision doesn't work because it takes 50 milliseconds for the signal just to get from the retina to the back of the visual cortex. Okay, so and even the pathway directly to the superior colliculus takes 50 milliseconds. So it would get too late to be able to get to the superior colliculus, turn off something in the superior colliculus. It's not fast enough. So the only other choice, another possibility, it's coming from here. Okay? And that is the correct choice. So this thing here is the signal for the quality of discharge of all your eye movements. So the brain sends a signal to move the eye, and the copy of this movement is stored here inside this reverberating circuit. So the eyes move like a guided missile. This burst neuron shoots the eye off, and then the system relies on this signal to stop the eye. Okay? How does it do that? The other thing that you should note is that it seems odd that this would be the quality discharge. You think of quality discharge somewhere up in the cortex, but this is a good place to place it, because not only do saccades enter this thing, but we saw the VOR entering this thing. In fact, all the eye movement signals enter this thing. So anything that moves the eye goes through this as well. So this is a good internal estimate of how much the eye moves. It's better than that coming from the spindles. It's much better than that coming from the eyes. And where does it go? Well, the neat thing, or one theory anyways, is a fellow called Doug Munoz. He's a good friend of mine. He's in Queen's University, and many years ago he proposed that this signal here is your internal estimate of where the eye is. Sends a signal to the superior colliculus, moving this hill of activity from where it started over to your fovea. So then as the eye moves, this hill moves, and when the eye gets to the target, the fovea is pointing at the target, it activates this part of the superior colliculus. That then activates these omnipause neurons, and that stops the PPRF, and that stops the saccade. So it's a nice internal feedback system, an internal guidance system for making these ballistic movements, like firing a rocket, to stop it in the right position. It's a neat system. Now, you remember how the signal got to the superior colliculus. So there was these neurons that came from the periphery to the superior colliculus and then to the PPRF. They also go to the visual cortex. Now, from the visual cortex, you have this other pathway that we looked at before, to the parietal eye fields, to the prefrontal cortex, and then the frontal eye fields. So the prefrontal cortex stores working memory. So it's got a map of where everyone is in this room, and when I want to look around at you individually, I remember roughly where you are, and I can make a saccade, a voluntary saccade. And then I activate the frontal eye fields, and I make these voluntary movements to you. But that signal, too, goes through the superior colliculus and through the PPRF. But it, of course, it has this longer pathway. It has a longer latency. Okay. Well, as with any other movements, the cerebellum is involved in calibrating them. we saw the cerebellum was involved in calibrating the VOR. Well, it's also involved in calibrating saccades. So let's look at these eye bulbs. These are saccades, and the eye, as we saw before, moves equally to the side. Okay? Now suppose this muscle were damaged for some reason. Okay? It's called a palsy. And when it does that, you can see that this eye's pointing this way, but this eye's pointing slightly different position. Were that to happen, you'd see double. Okay? One eye would be pointing there, the other eye would be pointing there, and the two images would be different on the eyes. And so that a patient that has that problem, seeing double, is called strabismic because of this problem in this muscle, or maybe some other motor neuron going to this muscle, or some other problem. Well, what do you do with such a patient? Often this problem persists because the system sort of ignores this eye. So the system then starts relying on the good eye and blocking the signal from the weak eye. So what often is done is to put a patch over the good eye, surprisingly. And what that does is forces the brain to produce a bigger signal to the weak eye muscle. Okay? And gradually this eye muscle gets a bigger and bigger signal, and then makes this normal saccade to the right target. Okay? But you notice what's happening under the patch. This eye is moving now too far. So, the surprising thing is that when you take off the patch, this weakened eye remains good because it still gets a stronger signal. And the brain instead teaches this stronger eye to move less. Okay. And does this through the vermis of the cerebellum. Now, this palsy will persist if it exceeds the capacity of the cerebellum, so that if you've got a complete palsy, nothing's going to help you. You didn't have a muscle there. There's no amount of input that would get you the right stuff. The other possibility is that the cerebellum itself gets damaged. Okay, let's look at nystagmus. Nystagmus is sort of this type of eye movement going back. The eye is going back and forth, back and forth. But you notice that there's the two movements aren't equal. One movement's slow and the other movement's fast. Okay. Now you can see this turkey in my backyard doing much the same thing. Okay. It's going fast, slow, fast, slow, fast, slow. Now, during the slow part, okay, it's stabilizing, its head is perfectly stable. It's moving back on its body as it's walking forward. And as a consequence, the image on its retina is perfectly stable. And then it makes this fast movement, which is like a saccade, to a new position. Okay. So the same thing will happen in any view if you turn round and round. The eye will move as far as it can, rotate as far as it can, like that head on the turkey, moving back as far as it can. And then when it can't move any further back, or your eye further to the extreme position, you'll flick over, make a saccade to the opposite direction, and again lock in on the world and keep it stable as you turn your head. Now notice here that the beat changed, okay? It's slow and then fast. What's happening while it's fast? Well, what you're trying to do is look in the direction you're turning, so you don't allow the slow phase or the VOR to persist as long as before. You make more frequent saccades in the direction you're turning. Now, here you see very similar movements, but there's a big difference. Okay? The head isn't turning. Okay? The head isn't turning, so somehow the brain is producing the same movement. And recall the VOR works in pairs. So the afferent from one side interacts with the afferent on the other side. Well, the question here is, where is the lesion? It's in your vestibular system, probably, because that's probably what's causing the same thing that's produced when you're turning your head. But in this case, the head isn't turning. So what's producing the same eye movement? Yes? Well, no, but here the head never moved, and it's I agree that when you turn for a long time, your cupula stabilizes itself, and you can get nystagmus when you stop moving. Yes. On the left horizontal canal. Yes. Let's see why. Okay. Well, if the signal is less on this side, then it's more on this side. Okay. So if there's little less signal coming from this canal, then now there's more coming from this canal. Well, what happens when you turn to the right? There's more signal coming from the right canal than there is from the left canal. So that's exactly what's happening here. Okay. This is, again, nystagmus, but it looks different. Okay. Here the eye is looking one direction, then the other direction. In each case, it's coming back to the center. Okay. And this is called by the lesion, the PPH, the signal that holds the eye in this eccentric position. Okay. But again, it produces something that looks like nystagmus, but it's different in that it has this exponential shape. Okay. It's not continuous as we saw before, but sort of starting out fast and going slow, more and more slowly. And then it switches directions. If you look one direction, it comes back to here. If you do the other direction, it still comes back to center. Okay. Here's Vergence movements. You can see, this is what the eye sees, okay? You can see that every time this ball moves from close to far, okay? Every time the ball moves, initially you can see it's different on each eye, okay? This is the fovea. There's an image that appears over here on this side, and on the opposite side of this eye. So it's got a retinal disparity. The signals aren't equal on the two eyes. That retinal disparity is, signals that a change in depth. Remember from a very early lecture about retinal disparity, giving you a sense of depth. The other thing that you can see is that it's blurred. There's a blur to it. Okay? Because it's moving from near to far, you've got to refocus. You can see the shape of the lens changing. Okay? So it's set for near, now it's set for far, now it's set for near, far. Okay, the other thing that you can see, and this is rather unexpected, so that change in lens property is what clears up the blur. But the other thing that you can see, this black thing here is the size of the fovea. And at the beginning of each movement, okay, it changes shape. Okay? Remember, the fovea, if it becomes small, reduces the blur on the back of your eye. Okay? It makes whatever blur is there smaller. So all three things happen at once. You turn the eye because you eliminate the disparity. You do accommodation or changing the lens properties. And you make the pupil smaller. Now, in the brain, there's two signals then. A blur signal that causes a Vergence movement, and a retinal disparity that causes a Vergence movement. At the same time, there's a signal to the lens to adjust its thickness. Again, it comes from the brainstem. You see a blur, that adjusts the lens thickness. But surprisingly, also does a signal for the retinal disparity. So both these things happen quickly when both of these things occur. If only one of them occurs, both these things happen more slowly. Yes? No, the pupil size. Yeah, I might have misspoken. Yeah. Thanks for correcting me. Okay. So, pursuit. We're trying to pursue this bee. Okay? Now, the pursuit signal comes from the eye, goes to V1, goes to MT, then there's two parts to MST. It goes to MSTL, the part that's interested in small objects moving on your eye. And so all these signals, notice that there's a retinal slip of a small object. From there on, the signal goes to the cerebellum and the brainstem. And from here on in, it's not sending out the retinal slip, but the speed of the eye movement the brain wants to make. So lesions of this structure will produce deficits in your smooth pursuit or anywhere else along this pathway. Now, if you look at the smooth pursuit movement, okay, here we start off with the bee stationary. Okay, then we can see here the bee jumps. Well, the will jump to the side. Okay, so it moves to the side. Here we saw the pursuit system. Well, backtrack. Okay. Moves to the side. Now. So it's pursuing then. Then it makes a quick saccade to while it's making the pursuit movement, it's still not on the fovea. Okay. So it needs to make a catch-up saccade to put the bee back on the fovea. So during this delay, the bee moved. The pursuit movement matches the movement of the eye to the speed of the bee, but it's still off of fovea because it had a head start on you. And so you generate a saccade to put the bee back to where the fovea is, and then you continue to pursue it while the bee flies. So it has those phases. Now, there are situations, like you can see here, if you wanted to, you could imagine there's a center to this. This is a wheel. These are two lights on a wheel. And you try, except for my hiccup in animation here, I couldn't quite fix the little hiccup occurs right here. You can try pursuing this. So this is an exception. And there's several other exceptions. You can train yourself to follow an auditory signal, a bee buzzing in front of you. Or you can close your eyes and move your eyes slowly back and forth, and you can train yourself to follow that movement. But as a general rule, without all this training, as you saw yourselves, that you cannot make a pursuit movement without a moving object. Now, if you look into the eye, magnify things, a whole bunch of amounts. So if you're reading anywhere, the screen, this screen, or a piece of paper in front of you, this is the size of a letter A you would see in a typical print. And that'll be projected back onto your fovea. And you can see here a whole bunch of cones that are looking at this letter A. But surprisingly, the letter A isn't stationary on your fovea. Okay? So here's the real surprise. There's tiny little eye movements, the little flickers of the eye, and then little drifts of the eye that are constantly moving this letter A on the back of it. They're very small, but compared to the size of your cones, they're quite large. Now, the really amazing thing is that if you stabilize the eye, so if you measure the size of these movements, okay, and move the A just the same size as these movements, so you keep the letter A stable on your fovea, the letter A will disappear. So for some reason, the brain needs these small little movements for vision, and we don't quite understand why. So, I'll just finish off and summarize it. We had 5 types of eye movements. You can divide them up into old ones and new ones. The VOR and the optokinetic reflex are old ones. Saccades, pursuit, vergence are new ones. The job of the old ones is to keep the image stationary on the entire retina, okay? Something big that's happening in the world. The world must be moving, okay? So the VOR and the optokinetic reflex help you keep these images, the whole world, stable on your retina. We saw the VOR is fast because it's a short reflex. So every time you turn your head, you have to move your eyes, and that's fast. But it responds poorly to prolonged rotation because the cupula springs back. And the VOR is calibrated by the cerebellum. We saw also that the optokinetic system helps the VOR. This reflex is slow, but that's good because the VOR is fast. And it, like the VOR, needs something on a full field, so on the visual system, to elicit it, and thus elicit this sense of self-motion. In terms of the new system, the first one is saccades. They point the fovea at the target. They're very fast and usually very accurate, and they minimize the time it takes to make the movement. But you have no voluntary control over its speed. You can decide what you want to look at, but you can't decide You decide to make it slowly or quickly, as you saw. The pursuit system it keeps the fovea on a moving target rather than a still target. Saccades are for still targets, but the moving target, this is for moving target. Now, someone bright will say, well, you made a saccade on that bee, right? And that the bee was not a still target, it was a moving target. But when you made that saccade, the bee was stable on the retina. The pursuit system had kicked in, and then you made the saccade. Now the pursuit is slower than the VUR because it's got more synapses, so it's less able to reflexively stabilize your eye. But you usually need a moving saccade. And finally, Vergence, it moves. You've got a problem that you have two fovea, so you've got to point one eye differently from the other eye. It prevents double vision or diplopia, so your Vergence system usually kicks in if your two muscles aren't working exactly properly, and they move the eye in opposite directions. And that's it. Thank you.